Swayam Prabha. Digital India. Educated India.
Okay, so we will be continuing with our discussions which we already had started in the last class. We were trying to derive the condition of choking considering the two phases separately, and we had also assumed or we had also considered the change of phase. So, that at one go I can make the whole derivation and then you can make the appropriate simplifications as and when necessary. So, if you follow what we had done till the last class, you will find that what we did, we finally arrived at a momentum equation for phase 2. Okay. In the same way, we can write down a momentum equation for phase 1 as well. Just write it down, let us see what you get in this particular case. Same thing we get minus dp dz in this particular case 1 by rho 1 u1 square 1 minus u1 square by a1. Now, in this particular case it was 1 by 1 minus x. So, therefore, it is minus dx dz, is not it. Here if we write it down, this is going to be 1 by 1 minus x minus dx dz. This will be 1 by a dA dz, again minus 1 by 1 minus alpha d alpha dz, if you remember, again plus 1 by rho 1 u1 d dz of rho 1 u1. Remember these things? Just instead of this equation of continuity, I am taking this particular equation of continuity. So, therefore, in this particular case also, if we write u1 d dz of rho 1 u1, we would get minus rho 1 u1 square by 1 minus x dx dz. Again here minus rho 1 u1 square by a dA dz. In this case plus rho 1 u1 square by 1 minus alpha d alpha dz, right. So, see, even if there are two phases and we are doing the same thing for the two phases as well, there is some minus plus sign here. So, there are plenty of scopes for you to do careless mistakes and plenty of scopes for me to cut marks. So, these things you are supposed to remember, otherwise I would not have elaborated the calculations here. Just to tell you that do not do things blindly, even if you are doing it blindly also, you must use some of your common sense for doing it. Okay. So, therefore, in the same way if we write it down, just look out whether I am doing any mistakes or not. So, it becomes minus 1 by 1 minus x dx dz minus 1 by a dA dz, then plus 1 by 1 minus alpha d alpha dz plus 1 by rho 1 u1 square rho 1 g sin theta. Then this will be minus, remember, f12 minus fw1 by 1 minus alpha phi, because f12 was positive for phase 2 and negative for phase 1. If you remember the direction of position as we had taken, plus that 1 minus eta by 1 minus alpha, that particular term g dx u2 minus u1 and this term, fine. Okay, I will write it down, u2 minus u1 g dx dz, agreed. So, for phase 2 we have got one particular equation, this is the equation for phase 2. This equation we had already got in the last class, this particular equation for phase 2, and a similar equation we have obtained for phase 1 as well. Now, if you compare these two equations, what do you get? You find that both these equations, they resemble one dimensional steady flow single component compressible flows, is not it? If you just compare these equations with this particular type of equation, you find that if you see the transparency, you are going to see that in this particular case also you have something of this sort, and there is a wall shear stress. Here also if you find there is one F12, if you see the F12 plus Fw2, here you have got a rho g sin theta, here also you have got a rho 2 and rho 1 g sin theta. Then in this particular case you have got a dA dz term, and in this particular case also you have got a dA dz term. What is extra here? Extra in this particular case which you get is number 1 the effects of phase change dx dz terms, and the other one is dx dz then eta all these terms, and the additional degree of freedom which is introduced by alpha. Other than that, if you find, if you compare this with single component compressible flows where we had performed a one dimensional steady state analysis, remember that we have done for all the cases. So, if we compare this, we find that in that particular case also we had something like the frictional component, where the frictional component comprised of only the wall shear stress. In this particular case we also have a frictional component which comprises of both the wall shear stress as well as your interaction between phase 1 and phase 2. Then we also have some additional terms which came up because phase change occurred. Here also in this particular transparency or in this particular presentation we have got some particular gravitational component, we have an identical gravitational component here. Here we have some area change term, in this particular case also we have a area change term. What extra we have? Effects of phase change and effects of your the additional degree of freedom introduced by alpha. Okay. So, from this particular, see this expression and this expression, if you see the left hand side, except for alpha, this 1 by alpha d alpha dz, all the excepting for this alpha, more or less all the other terms they are free of alpha, or in other words they will not change with any particular parameter of two phase flow. On what they depend? They depend on area change, they depend on physical properties and so on and so forth, isn't it? So, therefore, from here, just as I was discussing in the last class, that we can get the condition of choking for phase 2, we can get the condition of choking for phase 1. Where the problem starts? The problem starts that this alpha, it keeps on adjusting itself. So, that just now if we simply add up the two equations, we will not get the condition of compound choking, because there is going to be an alpha variable, and this alpha variable it will be adjusting itself according to d alpha dz, and therefore, we unless we can eliminate this d alpha dz, we cannot arrive at the condition of choking. Now, just observe these two equations and tell me how to eliminate d alpha dz from this equation and from this equation. If we eliminate that and then if we add the two equations, then probably we can arrive at a condition of compound choking. So, what we have to do? You have to multiply the first equation with alpha, the second equation with 1 minus alpha, and then we can add the two equations. Let us do that and let us see what we are going to get for that particular case. Once we can do it, it is expected that we can arrive at the condition of compound choking for that particular case. Okay. So, let us do this particular addition and then let us write it down and then let us see what are the things that we are going to get. So, for that particular case, the thing which we are going to get is minus dp dz alpha by, we are just multiplying one equation by this, this will be equal to alpha by x dx dz minus alpha by a dA dz minus d alpha dz plus alpha by rho 2 u2 square, again rho 2 g sin theta plus whatever was there inside that will remain intact, u2 minus u1 g dx dz. Fine. Same way the other equation, this was for, we are doing phase 2 first because it has alpha x. So, we have to write less in that particular case. in this particular equation for phase 1, what do we get? To 1 minus alpha by rho 1 u 1 square into 1 minus u 1 square by a 1 square. This is equal to minus 1 minus alpha by 1 minus x. Do it very carefully. You can come, instead of looking from me, you can write down from the expression which you have derived in your notebook. That will be easier for you. Plus 1 minus alpha by rho 1 u 1 square rho 1 g sin theta, just like I had got in the previous, this is minus f 1 2 minus f w 1 plus 1 minus eta by 1 minus alpha u 2 minus u 1 g dx dz. Okay. So, therefore, this is for phase 1. Which one? Sorry, by 1 minus alpha, very true. This alpha will be cancelling out at the end, very true. Thank you very much. This is 1 minus alpha, true. Okay. So, and finally, this 1 minus alpha will cancel here also, alpha cancels out. Okay. Now, if we add the two, simply after this we can add the two equations. This term will get cancelled out, minus d alpha dz plus d alpha dz, it cancels out, isn't it? And then what do you get in this particular case? Minus dp dz alpha by rho 2 u 2 square 1 minus u 2 square by a 2 square plus 1 minus alpha by rho 1 u 1 square 1 minus u 1 square by a 1 square. This whole thing, this will be equal to, first if we start adding this alpha dA dz, and here also we have 1 minus alpha dA dz. So, therefore, alpha plus 1 minus alpha, it becomes dA dz. Okay. So, by adding up this particular term and this particular term, we get minus 1 by a dA dz, correct. Same thing if you take the rho 2 this particular term, this g sin theta, and if you take this particular term. So, then in that case what do you get? Plus g sin theta you can take as common, and this is alpha by u 2 square plus 1 minus alpha by u 1 square, correct, plus f 1 2 if you take 1 by rho 2 u 2 square minus 1 by rho 1 u 1 square, agreed, plus f w 2 by rho 2 u 2 square plus f w 1 by rho 1 u 1 square plus whatever dx dz terms you have. There is one dx dz term here, everything concerning dx 1, and this is the other thing, and again this is one dx dz, this is another dx dz. So, we can combine, fine. We have written the dA dz terms, we have written the g sin theta terms, we have written f 1 2 terms, we have written f w 2, we have written f w 1. Now, remaining is the dx dz terms. Okay. So, therefore, this plus dx dz into alpha by x minus 1 minus alpha by 1 minus x plus g u 2 minus u 1 1 minus eta rho 1 u 1 square plus eta rho 2 u 2 square, agreed. So, therefore, this has come to 2 pages. We have this particular equation, this left hand side equals to this whole right hand side. Now, you tell me from this particular expression what will be your condition of choking under the present case. What is the condition of choking? Again in the same way, if you consider, we find that the term which is associated with dp dz, that will go as the denominator, and therefore, this term when I make this equal to 1, then it this term becomes equal to 0, because this corresponds to 1 minus MATP square. So, this term equal to 0 corresponds to my case of the condition of compound choking. Agreed? So, therefore, if you can tell me what is the condition of compound choking, this is alpha by rho 2 u2 square into 1 minus, if you just see your the term attached to your pressure gradient, you are going to get it, minus u1 square by a1 square. This was the term which was attached with the pressure gradient term. Okay. So, therefore, if this particular term, this is nothing but 1 minus MATP square, isn't it? And this 1 minus MATP square equal to 0 gives you the condition of choking. So, therefore, this term when it becomes equal to 0, it should give you the condition of compound choking. So, therefore, condition of compound choking is this is equal to 0. Now, look at this particular expression which I have got. Now, in this particular expression, if you see alpha 1 minus alpha, both are positive quantities, yes or no? Rho 1, rho 2, can they ever be negative? U1, U2, they cannot be negative. So, therefore, something plus something, if it has to be equal to 0, then how to adjust for that? Only the terms in the parenthesis, they can only be all other factors, since it is positive. So, only the terms in the parenthesis, they can be adjusted to give us the condition of compound choking. So, from here you can very well understand when we will have compound choking for the case of your from the two fluid model, when one of them is less than 0, the other of them is greater than 0. So, that they cancel out one another and they give us the condition of compound choking. So, therefore, now can you tell me when we are going to have the compound choking as derived from the two fluid model or for the separated flow of two phases? When this particular term, this is nothing but Ma2 square, this is nothing but Ma1 square, correct? So, therefore, we can have compound choking when Ma2 square less than 1, Ma1 square greater than 1, or Ma2 square greater than 1, Ma1 square less than 1. Only under that condition we are going to have. So, therefore, if both of them are either both of them have to be equal to 0, definitely under that condition we are going to have choking. So, therefore, one thing is for sure, when both the phases are flowing under choked flow conditions, definitely we are going to have compound choking. This is for sure. Okay? Both the terms are individually equal to 0. Otherwise, if one is supersonic, the other is subsonic, or vice versa, we can have the condition of choking. But provided what are the things that we have assumed here? Again, neglecting flashing, number 1, and the number 2, if you notice this equation, you are going to find out. First thing is, I have neglected the dx dz terms. I have assumed dx dz to be constant. Okay? For flashing, again in the same way, this x will be a function of h and p. This is first assumption. The other thing is, I have assumed F12 also to be independent of your pressure gradient. This is more or less a reasonable assumption, but I have assumed that the interaction between the two phases, they are independent of the pressure. Okay. So, therefore, this gives you the condition of compound choking assuming or considering F12 and dx dz to be independent of pressure gradient. Under this condition, we have got the condition of compound choking. Now, tell me, for flashing what is going to happen? For flashing, suppose we consider flashing, then in that case what happens? For that particular case, we can write x is a function of enthalpy as well as pressure, isn't it? Or in other words, dx dz, just like I had written down in the previous class, constant p plus del x del p at constant h, sorry, this is dh dz, this will be dp dz. Same thing we had done, and here this, what is this term, del x del h at constant p, or in other words del h del x at, this is equal to 1 by lambda, 1 by h12 we call it, very correct. This is 1 by h12. Okay. So, therefore, this reduces to 1 by h12 dh dz plus del x del p at constant h dp dz. Agreed. So, therefore, instead of this particular dx dz, we can write it down as 1 by h12 dh dz plus del x del p at constant h dp dz. Yes or no? So, for flashing what happens? This term along with this, it will go to the dpd, it is going to be attached with dp dz, and that entire thing will come out as the condition of flashing. Do you understand? So, therefore, for flashing in presence of for flashing, we find that we are going to introduce two terms. One is 1 by h12 dh dz, the other is del x del p at constant h dp dz. Okay. Now, the thing is, we can find out del x del p at constant h, and if the thermodynamic path is known, isn't it? Once we know that in what particular path we are going to affect the phase change, we can find out this particular term. Okay. So, this can be evaluated if thermodynamic path is known, isn't it? So, therefore, this particular expression finally for the condition of flashing, under the condition of flashing, the condition of compound choking, what it is going to be, we will just attach this particular term, this del x del p at constant h into this whole term will come as the exponent, or will come on the left hand side with minus dp dz, and this whole thing will be equal, has to be equal to 0. Agreed? So, if you just do it and then you find it out, we find we shall be noting that this will give us something like the condition of choking in presence of flashing. This will be for then alpha by rho 2 u2 square 1 minus u2 square by a2 square 1 minus alpha by rho 1 u1 square 1 minus u1 square by a1 square minus del x del p constant h into alpha by x minus 1 minus alpha by 1 minus x plus g u2 minus u1 1 minus eta by rho 1 u 1 square plus eta by rho 2 u 2 square, this has to be equal to 0. Do you agree with me, yes or no? Yes or no, do you agree with me? So, in absence of flashing, your condition of choking is given by this particular expression, and in presence of flashing, your condition of choking is given by this particular expression being equal to 0. So, we find that in presence of flashing, your choking should depend on the value of eta. This is a problem, because eta also we are not very confident how we are going to define it. Usually from thermodynamic analysis, that is quite an elaborate analysis, probably I will not be going through this, but from that particular analysis people have found out that eta equals to half. Okay, so, usually it is shared half and half by the two phases, but that comes under certain specific assumptions from thermodynamic analysis for isentropic conditions only. For other conditions, it is very difficult to derive eta. Okay. Under isentropic conditions for change of phase, we find eta equals to half. In other words, this particular force which is required to bring about a phase change is shared equally by the two phases. Okay. So, we find that in presence of flashing, the condition of choking is a function of eta, except just look at the expression and tell me under what condition choking will be independent of eta under flashing conditions. Is it clear to all of you what I want from you? You just look at this particular expression, the expression which I have written down, and tell me that under what conditions choking will be independent of eta for flashing conditions. When this particular term this disappears off, isn't it? When this particular term disappears off, it is going to happen. Now, definitely G cannot be equal to 0, U2 cannot be equal to U1. So, therefore, what can happen? Only your rho 1 U1 square can be equal to rho 2 U2 square. Under that condition, 1 minus eta plus eta cancels out. Clear to all of you? So, therefore, just remember this thing, condition of choking in presence of flashing depends on eta, except when rho 1 u1 square equals to rho 2 u2 square. Except for this condition, it depends on eta, correct. So, now I would like to deal with another type of very simple situation. Okay. See, whenever we find that the two phases they are accelerating through a nozzle, even for a single phase is accelerating through a nozzle. Okay. We have good amount of fluid in say any particular stationary tank, and then we have a nozzle connected to this. So, the fluid flows through the nozzle, a converging type of nozzle. Now, for that particular situation, which are going to be the dominating forces? Normally, the forces we have are gravitational forces, frictional forces and acceleration pressure gradient, isn't it? Now, for normal circumstances, when it is a vertical pipe, we know that even for single phase flow, we know that the gravitational pressure gradient is important. When it is a horizontal pipe, we know the frictional pressure gradient is important. Now, when it is flowing through a nozzle, say a horizontal nozzle, from a stationary tank, it is flowing through a horizontal nozzle. Under that condition, which particular pressure gradient or component is going to be important? Can you tell me? Acceleration. It is neither the gravitational nor the frictional pressure gradient. So, under such circumstances, under such circumstances, what happens? if we take up the basic equation of the basic momentum balance equation which I had written down, no, not this, yeah, this is the equation, the basic momentum balance equation, which this is the basic momentum balance equation, I believe. Yeah. So, if we look at the basic momentum balance equation under this condition, what do we find? There are just two phases which are flowing through a nozzle. So, under that particular condition, there is no change of phase. So, dx dz terms cancel out from both the cases, yes or no? Okay. And since acceleration pressure under these particular circumstances, more or less the phases, they do not interact, this interaction between the phases is not very important, neither is the interaction with the walls very particular important, correct. If it is a horizontal nozzle, then naturally this gravitational components also disappear off. So, under that condition, what remains? Your minus dp dz equals to this, minus dp dz equals to this. Okay. So, therefore, you find out that your equation of motion becomes very simple under this particular condition. For what happens? So, this is inertia dominant cases. Okay. So, for inertial dominant cases, what do we get? So, for this case, what did we get from here? Rho 1 u 1 du 1 dz equals to minus dp dz. Similarly, rho 2 u 2 du 2 dz equals to minus dp dz. Let us write down these two terms. What do we get? We get minus dp dz equals to rho 1 u 1 du 1 dz. This is equal to rho 2 u 2 du 2 dz. Yes or no? Correct. And now, in this particular case, suppose see what I have said, we start from a stationary tank. What is the initial velocity then? The initial velocity of fluid 1, fluid 2, it is 0, is not it? And then under such circumstances, if we assume that more or less rho 1, rho 2, they also remain constant. So, under such circumstances, we find there is a particular relationship between the final velocities of the two fluids. Definitely, even if they start from the same initial velocity, their final velocities are not going to be the same. Okay. Now, what is the relationship? Can you simply derive from the equation of the momentum equation that we have written down in this particular case. Now, this was again I will write down the assumption so that you do not forget. Same thing, please write down these assumptions in your exam, otherwise steady state one dimensional flow without phase change. Under this particular condition, if phase change would have been there, then we could not have written such a simple equation. So, this equation has been written under the conditions of steady state one dimensional flow without phase change, such that the f's are 0. The g containing terms are also equal to 0, agreed. So, therefore, we have obtained this particular equation. Now, assuming say u1 I initial, this is equal to very low velocity 0, u2 I equals to 0. So, therefore, with all these and rho 1 rho 2 equal to constant. So, therefore, under that circumstance, it is very easy to integrate this particular equation, is not it? So, under that particular situation, what do we get? We simply get minus dp equals to rho 1 u 1 du 1, right. This is equal to rho 2 u 2 du 2, very correct. This is say from p 1 to p 2 or delta p, agreed. This will be from 0 to u 1 final, we can write it down. This will again be 0 to u 2 final, we can write it down. So, just if we perform the integration, what do we get? We get delta p, this is equal to rho 1 u 1 final square by 2, which is equal to rho 2 u2 final square by 2. Agreed? So, how are these final velocities? How are these the final velocities of the two fluids related after flowing through the nozzle, assuming that they had started with a very low initial velocity, they were almost at rest and the flow was occurring under steady state one dimensional flow conditions without any phase change or without much interaction between. Now, normally under these circumstances wall interactions we can neglect even for single phase flow situations as well. Okay. So, therefore, under that particular situation what can we write down? We can write down, so under this situation u1 final by u2 final equals to, can we write this down, yes or no? So, therefore, we find that the final velocities after expansion they depend upon their densities. This is a very simplified assumption, very simplified derivation we have got with a lot of assumptions, but more or less under normal circumstances they give us more or less appropriate results. Okay. So, therefore, we find that under conditions of starting with very low velocity and all the other assumptions that I have already stated, we find that the final velocity of phase 1 and phase 2 they depend upon the they are in the inverse ratio of the densities of the two phases. Now, since we know that rho 1 is much, suppose it is an air water mixture, rho 1 will be much greater than rho 2 and therefore, finally, what we find u2f will be much greater than u1f. Even if it is under separated flow conditions also, we find that the two velocities will be much different even when we assume that the pressure gradient across them is the same. Just because of the densities, this difference is going to occur. But of course, remember one thing, this expression this has really no universal validity and it is primarily true only under conditions. This is true only under conditions of rapid expansion at low Mach number. This is important. Just because at low Mach number only we can assume rho 1 rho 2 to be independent, or rather rho 1 rho 2 to be constant and independent of pressure. Okay, only under that condition we can assume this particular case. So, after this more or less what are the things we have completed? We have completed we had first started with the two fluid model, we performed the equation, or rather we wrote down the equation of continuity, we wrote down the equation of momentum for the two phases, then we combined them in several ways. From the combined equation what we did, we found out the condition of choking. After finding out the condition of choking, we found that the results can be misleading under certain conditions, particularly because del alpha del p, this is usually derived for low to moderate pressures where friction dominates inertia. Okay. So, therefore, after that what we did, we considered the two phases separately, but of course, we also considered the change of phase just to keep the matters much more generalized. Then from there we derived the equation of momentum for the two phases separately and then we combined them. Then we derived the condition of choking under these conditions and we derived the condition both in presence of flashing and in absence of flashing. The only thing which is left after this is the hitch which was there. If we consider the basic equation which we had already written down, the basic momentum combined momentum equation, where we had, I do not have it at the moment, where we had found out that the only unknowns in that particular expression was the frictional pressure gradient and the dependence of alpha with z or with pressure gradient. Okay. So, these were the two things that had to be found out. Usually there are several empirical approaches for finding this out in presence of, or rather in absence of certain better techniques. So, we would be going through those particular whatever empirical expressions are available and we will be doing them accordingly. But before we start that, today I would like to do a problem for you. I would just like to specify a problem based on the simplest thing that we have studied till now, that is flow of an air water mixture through a nozzle. Just based on that, I would just like to discuss a problem simply to show you how flexible or how much depends upon the design of two phase systems. Okay. Just to show you that, I would like to do a problem, and in the next class we will be discussing the different methods of evaluating the frictional pressure gradient and the void fraction for two phases to be in separated flow conditions. Okay. Now, let us take up the problem. Now, say we have a very large tank, okay, and in this particular tank, from this particular tank, air and water mixture, they are flowing out. Okay. From a very large tank, air water mixture is there in this particular tank, and it is air water mixture flowing from a large tank through a nozzle. Now, the flow rates, they are more or less, and this particular this final diameter, that is 6 centimeter square. Okay. The nozzle, more or less, it is the diameter, sorry, the cross sectional area is 6 centimeter square. Okay. A equals to 6 centimeter square, and the flow rates, I have the flow rates, your Q air or Q2, this is equal to 0.04 meter cube per second. Q1 will be equal to, it is 4.5 into 10 to the power minus 4 meter cube per second. Okay. So, this is all. Now, what you are required to find out? You are required to find out, 1, pressure in the tank, and 2, you are required to find out the exit velocities, that means u1f and u2f. These are the two things you are required to find out. Okay. And pressure in the tank, that means P initial. Achha, one more thing is given, that is the exit pressure is atmospheric pressure. So, therefore, this discharges at atmospheric pressure. Okay. So, therefore, Q2 Q1 P exit equals to 1 atmospheric pressure, and T, the temperature, more or less it remains constant at 27 degree centigrade. So, these are the data which has been provided to you. Okay. Q2 is provided, Q1 is provided, and it discharges at a pressure of at an atmospheric pressure at a temperature of 27 degree centigrade. This is also given. So, what you are required to find out? You are required to find out the exit velocities u1f, u2f, and the pressure Pi in the tank. Okay. Pf equals to 1 atmosphere, it is given. Just this much is given, nothing else is given. How to proceed? What do you suggest? How should we proceed to do this particular problem? See, if you go through the problem very well, you will find that in the present form, the problem cannot be solved just like that, because in order to solve the problem, we first have to know how the two phases are mixed together and what is the flow pattern under which it is flowing inside the nozzle. Just if it would have been only water flowing or only air flowing, we could have done this problem. But since in this particular case it is an air water mixture flowing, so therefore, before we proceed, what we are supposed to know? We are supposed to know that how the two phases have been mixed together and what is the flow pattern that is being exhibited in the nozzle. Unless that is given, we cannot solve the problem. So, what we can do? Under the present circumstances, we can take the two extreme conditions. What are the two extreme conditions? One is the two phases are intimately mixed with one another and they are so well mixed that it becomes a homogeneous flow, and a homogeneous mixture flows out through the nozzle. This is one extreme. What will be the other extreme? The other extreme is going to be that the two phases, they do not interact at all at the interface and they flow in separate layers through this particular nozzle. Okay. These two can be the two extreme cases. Okay. So, what we can do? We can take up this problem, we can solve it first for two phases flowing separately, or we can solve it first by assuming that the two phases are flowing as horizontal flow. We can find out the pressure in the tank and the exit velocities. Then we can solve the same thing by considering that the two phases are under separated flow conditions with minimum interactions at the interface. Wall shear stresses can be neglected, probably in the problem also it will be specified wall shear stresses can be neglected. Okay. So, therefore, before doing anything, for suppose a problem of this sort is framed. So, therefore, you have to first decide the conditions under which it can be solved, and then taking up the individual conditions you have to solve the problem. Is it clear to you? So, for this particular case what we can do? We can solve the problem for two cases. One case is large forces between phases which suppresses relative velocity. What does this mean? That between the two phases such large forces are acting that they suppress the relative motion. What does it mean? What does this sentence mean? Homogeneous flow. Okay? Or in other words, this means that the two phases are under homogeneous flow condition. What is the next extreme that we can assume? No forces acting between phases. Naturally, when no forces will be acting between phases, they will separate out and they will be flowing in separate layers, is not it? So, no forces acting between phases. So, these are the two cases. This is the separated flow model. So, these are the two cases for which you can solve it. Now, let us take the first case when there are large forces acting between the phases. I will not be doing the whole thing, I will just be giving you the hints of how to solve it, so that you do it, come to the next class with the answers, and then only I am going to discuss certain other things which I have to tell you relating this problem. So, when the large forces acting between the phases, what can we assume? We can very well say that u1, u2, they are the same, no slip condition, and this is equal to J, okay, the volumetric flux, which is equal to Q1 plus Q2 by A. Q1, Q2 are already given, correct. So, therefore, from this what do we know? We know that if you see the homogeneous flow model, there you would find that minus dP dz was equal to a gravitational pressure gradient plus your frictional pressure gradient plus your acceleration pressure gradient. Now, in this particular case both these cancel out. So, therefore, your minus dP dz would be equal to minus dP dz acceleration. What was the expression of this particular case? This was nothing but g du dz, if you remember. Okay, this was equal to minus dP dz in this particular case. Okay. Or in other words, this g was nothing but equals to, this was G2 phase, rho Tp Utp du Tp dz. Yes or no? Agreed. So, therefore, in this particular case we found that assuming it, see, since the densities are more or less constant and it has been given and the pressure is not expected to fluctuate much. So, you can see you might be given such problems in your exams where maybe you have to make rational assumptions and then you have to progress depending on what type of assumptions you are made. Maybe if even if the assumptions are wrong, but if the logic is correct also you will be evaluated. So, remember these things, it will be much more analytical as compared to anything else. Okay. So, therefore, under this circumstance we can assume that it is incompressible flow, because water is anyhow incompressible. Air for such a small pressure drop it is going to be incompressible. Okay. So, for incompressible flows what we can write? We can just integrate this equation and we can have it as half rho Tp Utp square is equal to delta P. Rho Tp you can very well find it out, Utp also you can find it out, or else you can make this in a much more friendly form. What is it? you can write it down as half rho Tp UTP into UTP, this is equal to delta P. What is this rho U equal to? G. So, therefore, this is nothing but half G J or GTP JTP, yes or no? So, therefore, GTP is nothing but equal to your WTP by A or W1 plus W2 by A, JTP is nothing but Q1 plus Q2 by A. So, we can very well find out JTP, GTP and we can find out delta P. We know the final pressure as 1 atmosphere. So, we can find out the initial pressure. Very simple problem. For the second case, this was for the first case. For the second case, what we are supposed to do? Second case already we have derived the equation. Okay. So, the equation was minus dP dz was rho 1 u1 square by 2 equals to rho 2 u2 square by 2, is not it? In this particular case, we know what is u1 equals to j1 by 1 minus alpha, agreed. This is nothing but q1 by A into 1 minus alpha. Same thing u2, this will be equal to j2 by alpha, fine. So, instead of u1 square rho 1 u1 square, what can we write? We can write it as rho 1 j1 square by 1 minus alpha equals to rho 2 j2 square by alpha, sorry. Can we write down this particular equation, yes or no? So, once we can write down this equation, we can find out alpha as a function of rho 1 rho 2 j1 j2. Can we do this? Rho 1 rho 2 you already know, air water, okay. This is 1000 kg per meter cube and rho 2 you can take it down as 1.4 kg per meter cube, okay. J1 J2 you can find out. So, you can find out an expression of alpha using this particular equation. Once you can find out the expression of alpha, then once you know J1 J2, from J1 you can find out U1, from J2 you can find out U2, moment you know J1 alpha and J2 alpha, okay. You can find out U1 U2. Once you can find out U1 U2, these are U1 F, U2 F, because U1 and U2 initial was 0, correct. So, from there you can find out U1 F, U2 F. Once you know these two, from using this equation you can find out delta P, agreed. So, in the next class I would like you to come up with values of U1 F, U2 F as well as delta P, both for large forces such that it suppresses relative motion, and both for almost no forces such that there is lot of relative motion. Under both the conditions I would like you to solve it and then come up with the answers. Once you come up with the answers, I will be discussing why I have given you this problem, and then we will proceed for discussing the empirical techniques for wall shear stress and so on and so forth. So, next class please come prepared with the problems, or rather please do the problem and come with the answers so that we can make further discussions. Okay? So, thank you very much.